Hello, my name is Antonia Seifert and I want to thank you for your interest in my recent work. This talk is based on the paper called The Importance of Being Symmetric Flat Rotation Curves from Axisymmetric Static Vacuum Spacetimes, which can be found on the archive. Let's start right away with what we know best about exact axisymmetric static vacuum spacetimes. That's the Schwarzschild solution. Let me write down the Schwarzschild solution in axisymmetric coordinates, which looks like this. So the line element is given as a function of this capital phi, where this capital phi is the Schwarzschild radius over 4 square root of rho squared plus z squared. This for the time part. And then we have a factor 1 plus capital phi to the 4 for the spatial part, which we write in cylindrical coordinates. This line element is of the form that we have prefactors, positive prefactors, except for the time part where we have this minus signs. E through the 2a reflects a positive prefactor. For the time part, we have some coefficient for the radial part and the angular part having the same prefactor. And in the case of the Schwarzschild line element, we even have the same prefactor for the dz part. So for suitable B and A, these line elements agree. And from this one, we see that this spacetime is static, and this is why it is diagonal. We don't have any GOI components, and it is spherically symmetric, having the same coefficients here and here. It is, as a spherically symmetric spacetime, also axisymmetric. We can now alter this general line element by choosing only this coefficient to be different. So we use e to the 2h instead. And we can derive the vacuum Einstein field equations from this, giving some partial differential equations, which can then be solved. And these are the two line elements that I want to talk about today, and which I present in this paper. The first one I call the cylinder line element. For the Schwarzschild solution, we have 3 Killing vectors. One is the time-like Killing vector, reflecting the stationarity, which is then further specified to actually be static. We have the del phi Killing vector, and which reflects the axial symmetry, and the d theta Killing vector, which reflects the spherical symmetry. For the cylinder and disk solutions, which I want to present now, I stay with the del t and the del phi Killing vectors. So here we have Killing vectors del t, del phi, and del theta. For the cylinder solution, we have del t and del phi. So these are the Killing vectors, which reflect the symmetries. And for the cylinder solution, I choose a third Killing vector, being the del z coordinate vector, which means that the line element is independent of the z coordinates. And this is then given by ds squared is minus c ln rho over r, with r and c some integration constants. c squared dt squared plus b over rho squared square root of c ln rho over r, b again as an integration constant. We have the same prefactor for the d rho squared and the rho d phi. And by appropriately scaling the z coordinate, we find c ln rho over r again. The second line element that I want to present is what I call the disk line element. It is obtained from the cylinder solution by variation of constants, which is why it looks very similar, but we allow for a z-dependent epsilon function, which is not fixed by the Einstein field equations. By having this z-dependence, we only have two Killing vectors left, so del t for stationarity and del phi for the axisymmetric spacetime. The line element is then given by minus epsilon c ln rho over r c squared dt squared. We have some constant beta rho squared c ln rho over r. Again, rho squared plus rho squared d phi squared. And in the z part, we have another constant gamma, and then we find the derivative of the epsilon function squared times the epsilon function times c ln rho over r dz squared. We can see that we have a couple of singularities. We have a singularity in capital R, which can be thought of as a radial horizon. We have a singularity in rho equals 0. And depending on our choice of epsilon functions, we might, for example, get another singularity in z equals 0. That depends on the choice of epsilon. And plotting these horizons, the horizons for the cylinder solution look like this. And, well, for example, if we have a singularity in z equals 0, this is how the horizons for the disk solution look like. And this is why I call them the cylinder and the disk solution. Now, as I said, I care about rotation curves in galaxies. In galaxies, we assume velocities to be very low, so we just care about the low velocity approximation to our metrics. And in the low velocity limit, we can determine the coordinate acceleration which is related to the acceleration with respect to proper time, which is related in turn to the geodesic equation. And from the geodesic equation in the low velocity limit, which means that we only care about velocities having only about the zeroth component of any velocity, because the others are too small to be relevant. From this, we obtain, so this is from the geodesic equation. And the e to the minus 2a is for the general form of the metric, and that's the substitution from tau to t, so proper time to coordinate time. From this, and relating this Christoffel symbol to the metric, we find that our coordinate acceleration in the k component of that, so like this, is given by c squared over tau del k GOO. And, or if we write it in 3 vectors, that's some coordinate acceleration is minus the gradient of some effective potential, which we define up to a constant to be c squared over 2 GOO. We can then, from this acceleration, consider rotational motion, which has from some central force the acceleration v squared over rho in the z equals 0 plane only, which we assume to be equal to the absolute value of our gravitational acceleration, so gravitational coordinate acceleration, which leads us to the rotational velocity given by this absolute value times the rho coordinate. We can do this for the Newtonian approximation to the Schwarzschild solution, and we get back for the effective potential the Newtonian potential. I will not derive this here due to time issues, but you can find this in the paper as well. And from this, we find that our rotational velocity is gm over rho. This is why Newtonian Newtonian gravity is not able to explain flat rotation curves, because we find this 1 over square root rho here in the rotational velocity. So that's for Newtonian. While for the cylinder, and similarly for the disk solution, we find the effective potential to be some constants times the logarithm of rho over r. R is our horizon, and thus the rotational velocity is just these constants, which means that it is indeed flat. And we can see this, for example, here. These are plots for the acceleration as a function of the Newtonian acceleration. Okay. And for the rotational velocity. And you can see here that indeed the logarithmic potential, and this is indeed true for any logarithmic potential, gives flat rotation curves. We can also relate the asymptotic velocity, which is given by this constant, so the velocity over here, to the mass of the galaxy, and use this to fix the c constant, which will then be proportional from this power law. We find that it is proportional to the square root of the mass. Now, how does this relate to actual physical galaxies? The line elements that I derived are vacuum solutions, and they are static, so this is not physical. But it is at least as good as the Schwarzschild solution, because the Schwarzschild solution is a vacuum and static solution as well, and from this solution we get back Newtonian gravity, what we usually use in galaxies. Furthermore, general relativity is a local theory, so all of these metrics are only valid locally. So we can think of a galaxy, and we're somewhere in the plane, and we just look inside and see like there's something going on in both directions. We don't see the end. It looks like a cylinder, so that's where we might be able to use the cylinder solution. If we move further out and notice, well, we do have some z dependence, but still our mass distribution outside is negligible to what is in the center in a somehow cylindrical form, we can use the disk solution. None of these solutions do converge to the spherically symmetric Schwarzschild solution, due to the different symmetry conditions that can be thought of boundary conditions that we impose in the beginning to derive the solution. So that's imprinted in the ansatz, and we will not be able to change it throughout the spacetime if we just start with those. But we can think of that if we move far away, we will not notice the cylindrical symmetry anymore of the galaxy, so that is where the spherically symmetric Schwarzschild solution will become relevant again. Furthermore, we find that we can explain flat rotation curves in the low velocity limit. It is not for an extended source or anything, how we would treat it in Newtonian gravity, but it is an important step towards understanding flat rotation curves. And in this case, we don't even need dark matter. That does not mean that we rule out dark matter, but there is no need for it to explain flat rotation curves based on these symmetries. In particular, the main point that I want to make is, if we only change the symmetries and we leave everything else the same, having vacuum and static spacetime, this does change our physics, our equations of motions, even in the low velocity limit. And so symmetries are really important to be considered right from the start. Even if we want to take the low velocity limit at the end, we need to care about them and think of the symmetries of our system in the first place. And I want to encourage further research to consider where we have the missing mass problem, where we can actually think about symmetries to maybe help understanding that. In any case, we do not find a full spacetime manifold. As I said, it is only locally, so this is only a very tiny step towards the understanding of galaxies with the help of general relativity. But yes, I want to stress that symmetries are very important, and we need to consider cylindrical symmetry when we talk about galaxies.